Okay, so in this part of the video, I'm going to go over the pH calculations, relationship between pH and pOH. So maybe I'll just make a quick one for just 20 through numbers 26 real quick. And the first one gives us a perfect opportunity real quick to kind of review the pH scale before we even kind of start. Because it asks about if the pH of a solution increases by 2 units, so for example going from 1 to 3, then the ratio of the new to the original hydronium ion concentration would be which of the following. So this is the same kind of scale that I gave you guys over on the board when we reviewed this in class, but this is our pH scale. So all these numbers here, right, are all the pHs we have, and generally it's going to go from 0 to 14, even though technically there are some bases that can get a little bit above 14 and also some acids that technically can go below 0. But this pH scale, right, we have 7 that's considered neutral, and we talked about it in class, but it has to do with this whole pH scale is based on water and how water is always self-ionizing or auto-ionizing or self-protonating. That's kind of all saying the same thing. But water itself, like we talked about, is constantly going under that reaction with itself. And if you want, I guess I can kind of show that real quick here. Right? And again, these are notes I put up on Classroom 2. But water is constantly reacting with itself. We have like 2 water molecules that'll interact, and one of the oxygens from one will take the hydrogen from another one. And as a result, we'll get the hydronium ion, that's the H3O+, and the hydroxide ion. So this is happening constantly in water. So in water right now, there's neutral water molecules just hanging out. And again, there's 2 at a time all over the place that are constantly making the H3O+ and the OH-. But that H3O+ and OH-, right, every time those 2 water molecules interact and do that, or react and do that, we make one of those and one of those. So like those charges here, right, the positive charge from the hydronium, the negative charge from the hydroxide, those balance each other out and still cause water to be neutral. And I kind of broke down in my notebook the equilibrium constant for how this is happening, which again, that's just taking the equilibrium expression where we do the products divided by the reactants, and we kind of look at what's going on. So then if I took that same expression and wanted to do products over reactants for this one here, my products are hydronium and the hydroxide ion, and I have nothing here in the numerator because I have no reactants, because remember, we don't include any liquid reactants or products in the equilibrium expression. So the Kw expression is only the hydronium concentration times the hydroxide concentration, and these were experimentally determined by scientists, and it was found that in neutral water at any given time, the concentration of the H3O+ that's being made is 1.0 times 10 to the negative 7th, and the hydroxide concentration, right, is equal concentration at 1.0 times 10 to the negative 7th. So Kw is what's equaling 1.0 times 10 to the negative 14th. So the reason that 7 is what's considered neutral is because it's at that pH of 7 when we have, right, the same amount of hydronium and the same amount of the hydroxide ion. So if we end up with more hydroxide than what's naturally normally produced in water, we know that that solution is basic because we have more OH- that's present in the solution. That's what's right at that neutral point. Same thing for when we recognize when a solution is acidic, right? Neutrally, like water, the thing that we're dissolving it in, the normal amount of H3O+ that's floating around that solution anyways is right at pH 7, because there's 1.0 times 10 to the negative 7th of the hydronium ions floating around. So if we end up with more hydronium that's present in a solution, we know that there must be an acid present because that's more hydronium present than what the natural water is producing. So that's why 7 is considered that neutrality point here on the scale, is because again, it's based off of water, and like at 7 is when we have the OH- and the H3O+ concentration equal. So if we have more H3O+, we're acidic. If we have more OH-, we're going to be basic here on this line. And reviewing again real quick, like why do we use a pH scale? Why don't we just use, right, the concentration of hydronium or the concentration of hydroxide? Well, just like we talked about in class with the Ka and the pKa, Kas can get kind of ugly, but the pKa makes them really nice, normal numbers to look at, and it makes them easier to compare. Same thing with Kb and pKb, right? The pKb are way easier numbers, way more manageable numbers to deal with than looking at crazy scientific notation that the KB can be in. So it's the same thing for the hydronium concentrations, why we have the pH scale, right? Because a hydronium concentration, which is the same thing as an H plus concentration, because again, we talked about how technically the amount of H plus present in solution will always be equivalent to the excess H3O plus that's in solution, right? So if it's more than what water is naturally producing, any extra hydronium that's made would be due to the presence of H plus coming off of an acid. So I'm using these kind of two terms interchangeably. So when I say hydronium concentration, that's the same thing as the amount of H plus floating around in the solution as well. So these are technically why these could be written as the same thing here. Oops, I just kind of ran that into it. Didn't mean to do that. But sometimes you see the pH equation written this way instead of this way, but it's literally the same thing. Okay, but right, we're talking about, this is the concentration of H plus floating around solution, right? And we know that there are so many molecules at any given time in a sample, right? It's too crazy for us to even really imagine or think about as human beings, right? It's like an astronomical number. So these would also be some crazy scientific notation values if we actually literally counted the amount of particles that were present in that solution. So again, we take the negative logarithm of that number to actually kind of bring down that exponent and make it a little bit more manageable, right? And like by doing the negative one, we kind of turn any negative exponent positive and vice versa. So just to kind of give you an example of where this came from, right? Like let's say that you had an H plus concentration of 1.0 times 10 to the negative fifth, right? Our pH would be just 5, right? That's a way easier number to look at than this one up here, right? If our H3O plus concentration was 1.0 times 10 to the negative third, right? Our pH would be 3. That's a way easier number to deal with, right? So if we're comparing, right, like the acidity of one solution to the next, looking at numbers like 5 to 3 or 3 to 5, that's way easier for us to, think about, to manage, to make a quick comparison than trying to do calculations with scientific notation, especially considering they're usually never going to turn out to be nice, pretty numbers like the 1.0 times 10 to the negative fifth, right? Sometimes you're ending up with 2.679 times 10 to the negative something, right? They're not always as neat as these, right? So just making it way more manageable to work with, which is where this pH scale is coming from, right? Because you'll be able to calculate a pH and be like, boom, it's less than 7. I know that this is acidic, or it's more than 7. I know that this must be a basic or alkaline solution. And one thing I want to talk about, and we went over this a little bit in class, but let's just compare these two I did here with like a pH of 3 to a pH of 5, right? That doesn't seem like a lot, right? Like 5 to 3 or 3 to 5, right? But in reality, right, this pH scale is based on, right, like log base 10. So this is like on a base 10 scale. So going from something that's like a pH 5 to a pH 4, right, this is a difference of times 10 to the negative fifth and then 10 to the negative 4. So we're different here by a whole factor of 10. So like a solution that has a pH of 4 is 10 times as acidic as one that has a pH of 5, right? If we went from 5 down to 3, right, going from 4 to 5 was times 10, and from 4 to 3 again is a times 10. So like a solution with a pH of 3 is 100 times as acidic as a solution with a pH of 5. In other words, we have 100 times, right, the amount of H plus ions floating around. So again, 5 to 4, right, 10 times as acidic, right? 4 to 3, 10 times as acidic again. Therefore, 5 to 3, it's like 100 times the difference there, right? So you can imagine if we kept on going, right, we're just, again, like we're moving it on a whole base 10 scale. So this is pretty dramatic here. Okay, so let's go back to that number 10 that it's asking us about, because it wants us to compare the pH of a solution when it increases by 2 units. So increasing, we have to go bigger on the number scale. So we're actually getting less acidic as we increase pH, right? Because we want to be closer to 0 to be the most acidic. The closer you are to 14, the more basic you are. So it's saying in number 10 that we're increasing on the pH scale. So if we went up 2, right, it says that let's make a ratio of the new to the old, or the new to the original. So if we were making a ratio of the new to the original, right, and let's just say that the new one was 3, because it said we are increasing, and the original one was that 1, right? let's actually kind of look at what this means. Let's say that here's our original here. And this is like the new one that it wants us to do, right? We just went and decreased the acidity by a factor of 10. And then we decreased it again by another factor of 10. So we overall decreased this acidity by like 100-fold. And the reason that we're looking for this ratio here, or like the 1 over 100, not 100 over 1, was because like we're reflecting like this new solution here would be less acidic, right? And it's like 1/100th of the acidity of something that had been like a pH of 1. So that's why our number is going to be D, right, for 1 over 100, because that new solution is less acidic, right? Option A would be out too, because it's saying that you're twice as acidic, right? And again, we're on base 10, plus increasing pH does not, right, make you more acidic, right? This option was there to kind of trick you, right? Because it was dealing with the 101, but again, it's like the new to the old, right? The new one, right, is less acidic. So we're looking for like, it's going to be a fraction of what the original one was, right? This one, yeah, this one was a decrease, but every time you move one up, it's not just by half, right? We're talking about a factor of 10, right? And obviously it would not be unchanged there, okay? So let's go on to number 21. I'm just going to erase this stuff so it doesn't confuse anybody later when I refer to any of this stuff. And I'm sorry, I have some writing on here that I'll kind of go over, but I'll write this all bigger here later in a second. Okay, so 21, when the hydronium concentration is 1.0 times 10 to the negative 7th molar in water at 25 degrees Celsius then. So the reason it was mentioning 25 degrees Celsius is because that's at room temperature. And those experimental, right, hydronium and hydroxide concentrations of water were found at room temperature, right? That's like standard temperature. So that's just kind of saying like at equilibrium at room temperature, which is when all these values were found. And like we talked about a second ago when I was showing you my notebook, right? It's water is special and that its H plus concentration, which is the same as the hydronium concentration, is equal to the hydroxide concentration when it's at equilibrium at room temperature. So always for water, it's always true, like I just showed you guys my notebook a second ago, that the H plus, or we can call that H3O plus, is always the same as the hydroxide concentration in water, which is why C is the answer that we're looking for number 21. So number 22, when the H plus concentration is 4.0 times 10 to the negative 9th molar in water at 25 degrees Celsius then. So then obviously all our answer choices are pH. So it wants us to actually find a pH. Well, lucky for us, right, the pH equation, I'll write this out for you. I have it written here in purple, but I'll kind of write it bigger here for us. To find pH, we do the negative logarithm of the H plus concentration. So we 100% need the H plus concentration in order to plug in to the pH equation. And luckily it gave us what the H plus concentration was right there in the problem, 4.0 times 10 to the negative 9th. So for us to do this, let me just label this real quick, number 22. We have to do the negative logarithm of the 4.0 times 10 to the negative 9th. You're going to go right into a calculator, which will do this for you. We're going to do the negative logarithm of 4.0 times 10 to the negative 9th. And that's going to give us, let me actually write this whole thing out so I can show you how to run for sig figs with this. Okay, that's what your calculator says. Obviously, we can't have that many sig figs. So, something I want to make sure you guys understand, since the pH scale, each of these numbers, right, is based on base 10 movement, the main number of a pH, like the thing before the decimal, right, that number out in front is just a placeholder for like a decimal. It's like a base 10 movement. And we learned early on in the beginning of the year when we did sig figs, when we talked about scientific notation and sig figs, right? Like that base 10 movement, right? So if you have like leading zeros or like lagging zeros or those kind of things, those are just like placeholders for base 10 movements. Those don't count as sig figs, right? So each of these numbers on the pH scale are representing just a base 10 movement. It's not measuring like the accuracy of that measurement. So it's any number that comes after the decimal and the pH calculation that will actually be the sig figs, because the first number is just representing where you are in this base 10 scale. So when I end up with a number like this, right, I'm looking at the measurement that I was given, right, 4.0 times 10 to the negative ninth. The 4.0 is the number of sig figs that I have to consider, because the times 10 to the negative ninth, that's just that's a placeholder for the decimal movement, right? Those are base 10 placeholders. This thing doesn't count for sig figs. So the measurement that I was given that I had to find the pH for, I only had 2 sig figs of information. So when I calculate the pH, I can only have 2 sig figs of information. So again, the 8 does not count for sig figs in the pH scale, because that 8 is just a placeholder, right, for the base 10, and like letting us understand where on that base 10 scale we are. So we get 2 sig figs after the decimal in order to reflect the same accuracy as the 4.0 there in that scientific notation coefficient. So we'd have to round this to 2 sig figs after the decimal. So the 0.3979, yada, 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 that would round to 40 here. So that is why the answer is D. The pH is 8.40. Okay, let's go on to 23. 23, a solution with a pH of 9.5 has a pOH of, well, you guys should have your formula sheets with you at all times when you're doing any of these problems here. And I'll pull it up just so I can kind of show you where on this thing you want to be looking right now. It's the equation that I gave you guys in class, but it's also here on your sheet. The pH and the pOH will always equal 14. And again, that's because water, right? Like water has the same hydronium and hydroxide concentration that were each of the 1.0 times 10 to the negative 7th. So we got the Kw to be 1.0 times 10 to the negative 14th. So like that amount will always be equal to 14 when we actually do the negative logarithm of it. I'm just kind of explaining real quick where this equation is coming from. But the pH and the pOH will always equal 14. So in number 23, when it's saying, okay, it says a solution has a pH, or sorry, it has a pH of 9.5. And it just wants to know what the pOH would be. Well, we know that pH plus pOH always equals 14. So we have 9.5 plus the pOH equals 14. So we got to subtract 9.5 from each side there. I don't know why I did that on the calculator. I could do that in my head. But we end up with it technically should be just 4.5. The answer key is, the best answer is the 4.50. Oh wait, sorry. I didn't write that correctly myself. It did give us the pH of 9.50. So I actually get the extra sig fig here. This 14, by the way, this is oh, sorry, I'm like totally out of frame. This 14 that this equals here, that's like 0, 0, 0 to infinity, right? Like that's exactly 14 that the pH and pOH equal. So this is kind of like 14 with like an infinite number of sig figs minus 9.5. We get 2 sig figs after the decimal. So once we actually subtracted these, right, this 4 does not count for sig figs because that's just, again, the base 10 placement on the pH scale. So we get 2 more sig figs after the decimal, hence the 4.50, which is going to be option C. So 24, kind of run out of room here. Okay. It's getting a little trickier now, ish. Can you see it here? Okay. A solution with a hydroxide concentration of 1.20 times 10 to the negative 7th molar has a pOH and a pH of, well, it gave us in the problem only the OH minus concentration, which was 1.20 times 10 to the negative 7th. So this is all we have right now to work with, is what our hydroxide concentration is. So like I told you guys on Classroom, everything you need to do any of these problems are all here on this formula sheet. So I'm going to come down here to all the stuff with hydroxide, because this is helping me with all my base stuff. And if I have the hydroxide concentration, right, I have exactly what I need to actually plug in to this to get what the pOH is. And once I have the pOH, I can use this equation up here to calculate the pH, right? Because those will always equal 14. So I need just one of those values to get the other one. So what I'm going to do for number 24 is take advantage of the fact that we know that the pOH will be the negative log of 1.20 times 10 to the negative 7th. So we'll do that in the calculator. 1.20 times 10 to the negative 7th. Okay, I get 123 sig figs, because that's a concentration measurement, so all of that counts, right? This is not a pH, this is the whole thing right here. So I get, for my pOH, I get 3 sig figs after the decimal. That would be 6.921, because that 8 over here after the 0 would bump that up to a 1. So that's my pOH. So that's one of the things that the problem wanted. But then what's the pH? Well, I know the pH plus the pOH will always equal 14. So the pH plus 6.921 will always equal 14. So we can solve for the pH by just doing 14 minus 6.921. I get 3 sig figs after the decimal here, right, which would be this right here. So here's my pOH it's asking for. Here's the pH it's asking for. And that should give us the correct answer. I lost my page here. Which page was I on? Okay. So this one would be, the reason I don't have it circled on here is because none of the answer choices were actually to the correct number of sig figs. But for sure, 100%, you do get 3 here, because this here is 3 sig figs total, because that's an actual measurement. Oops, you couldn't see that. My bad. That's 3 sig figs there. So we do get 3 sig figs after the decimal for pH and pOH, because the first number before the decimal doesn't count. So I have to look for the closest answer choice for the correct answers, which are 6.921 and 7.079, which would leave us to A as our answer there. But if you were getting something different, right, it should be technically more sig figs than just that, but that is, right, one mistake that is in this, but that A is the answer. It's the only close one to what we got, but the correct answer that you guys should have are these numbers here, because you do get 3 sig figs, right, because pH and pOH is only after the decimal that counts for sig figs, and we're basing it off our initial measurement of that concentration, where all of this counts as sig figs here. Okay, so 25, let me get another piece of paper. $25. You can follow along on yours, but just kind of write it out here. 25 is saying a solution with a pOH of 4.3 has an H plus concentration of what? Right? So now this is a little tricky. Because it wants us to get an H plus concentration at the end of the day. So if we have pOH, right, what's our connection to H plus? Well, we have to look at our formula sheet, right, because everything, the answer to all these are kind of hidden somewhere in here. If we have the pOH, right, we can get the pH from this equation here. And once we have the pH, right, we can get the H plus concentration, which the problem is asking for, if we do 10 to the minus pH. So that's the relationship between those two, right? Because that's the opposite equation to the pH, right? So the pH is negative log of the H plus concentration. That means that the H plus concentration would be 10 to the minus pH. So we're going to use the pOH it gave us to solve for pH, and then we can raise 10 to the minus pH that we get, and it will give us the H plus concentration. So I'm going to use this equation first. The pH plus pOH equals 14. So the pH plus 4.3 equals 14. So we're going to get our pH first by doing 14 minus 4.3. And we only get one sig fig because the pOH, right, only after the decimal count. So it only gave us one sig fig here. So when I go to round this, I have to make sure that I'm sticking true to that. So my pH is 9.7. So now I can plug it into that formula that tells me what H plus is, which is 10 to the minus pH. So that means that H plus concentration should be equal to 10 to the minus 9.7. So we're going to do 10 to the minus 9.7. That gives us an H plus concentration of, all right, we only get one sig fig here because we were limited to that one sig fig there in the beginning. Your calculator is telling you 1.995. So technically to one sig fig, we do need to round this to just, 1.995 times 10 to the negative 10th. So we have to round that to 2 times 10 to the negative 10th for our H plus concentration. And as you can see in my answer key, or the answer for the problem set, I crossed off the, D is the answer choice, the correct one, but it said 2.0 times 10 to the negative 10th molar. And technically, and I forgot my unit here, bad me, you actually can't have that extra sig fig there after the decimal. Because in a concentration measurement, right, this whole thing is a measurement. Like this is like an actual real number. And in scientific notation, this whole thing counts for your sig fig. So 2.0 would mean that we had 2 sig figs, which we were not allowed to have because we were limited by just the one sig fig here after the pOH. So this is also, again, a mistake in his test, but the answer choice should be 2 times 10 to the negative 10th, but the only close one there was your option choice for D. Hence why D was the answer. Okay, 26. Which statement, A through D, is not correct? If all are correct, respond with E. Pure water at 25 degrees Celsius has. Well, I kind of derived this earlier, but what you can look at is your notes from when we did that, or look at the notes I put on Classroom for this. This is the page that you want to be looking at. I kind of went through and derived what all that stuff was for water. Because again, this pH scale is based on water. So what's true about water? Well, right, so it's saying like pure water, so nothing dissolved in it, 25 degrees Celsius, right, room temperature. So it wants us to kind of be talking about like what water can naturally do here at equilibrium. Right, the KW would be the 1.0 times 10 to the negative 14th. And if you don't remember, where's my pencil? That was because, right, here was our equation, right? There was 2 water molecules that were giving us H3O plus and OH minus. So our equilibrium expression was products divided by reactants. We were only allowed to include aqueous ones. Whoops, I forgot to put my state symbols. So you had the H3O plus times the OH minus, and those were each experimentally found to be 1.0 times 10 to the negative 7th. So when you actually multiply those out, that would equal 1.0 times 10 to the negative 14th. So that's why A is true. This is my hydroxide concentration at equilibrium. So that is my hydroxide concentration. So if I plugged that into the pOH equation and did the negative log of that, that would give me a pOH of 7, which we know is true because like I had told you guys before, right, the pH is 7 and the pOH is 7, hence why the pH plus the pOH will always equal 14. So for that reason, that's why we know that this is true, and technically D is true as well. And for water, at equilibrium at room temperature, right, the amount of H3O plus and the amount of hydroxide that's made at any given time is equal because those 2 water molecules are making 1 hydronium and 1 hydroxide every time this reaction happens. So it makes, for every 2 moles of water, we get 1 of these and 1 of these, so C is equal to. So that's why E is our answer choice, all of the following correct, and that is true for water and only water. So that finishes numbers 20 through 26. I'll start another video for the next segment.